In this video, I'll be explaining to you dynamic programming. Specifically, I'll go through the definition and the theory. Then I'll talk about how you classify different problems and understand if you can use dynamic programming for them. Then I'll get into a few examples where I explain how to implement dynamic programming, as well as how you can optimize otherwise poor time complexity solutions using dynamic programming. Now, I do want to mention that I do have a programming course. It's called Programming Expert. You can check it out from the link in the description. It teaches fundamental and advanced programming concepts, mostly in Python, but soon in some other languages as well as software engineering tools, software design, has over 100 videos, hundreds of practice questions, multiple programming projects. If you guys want to check it out and support me, please do from the link in the description. You can use discount code TIM. I think it's a great resource to get better at programming. Regardless, with that said, let's get into dynamic programming. So let me start here by reading the definition. Dynamic programming is an algorithmic technique for solving an optimization problem by breaking it down into simpler subproblems and utilizing the fact that the optimal solution to the overall problem depends upon the optimal solution to its subproblems. So this is a very general definition, and this describes a variety of ways of solving problems, but the key here is that we are breaking a problem down into simpler subproblems, and then solving those subproblems, and the solutions of those subproblems are going to lead us to the solution of the overall problem. Now, this can be tricky because sometimes you can have problems that can be broken into subproblems. However, the solutions of those subproblems do not necessarily lead you towards the optimal solution of the overall problem. So optimization problems really involve finding the best answer out of multiple answers, and you'll see dynamic programming is used many times when you're trying to maximize a value or minimize a value, or again find the best answer out of a variety of different answers based on whatever criteria that may meet. Now, you can use dynamic programming for problems that are not optimization problems or not by definition optimization problems, and I'm actually going to show you an example of that right now. So to better illustrate this, because I understand it's still probably confusing, I'm just going to go through the famous example, which is the Fibonacci number sequence, and discuss how we solve that problem, why we can kind of write this as a dynamic programming problem, and then how we optimize the solution using dynamic programming. Then I'll get into a much more advanced example, so stick around if you already understand this example. Anyways, the Fibonacci sequence of numbers is a very famous sequence that looks like the following. We have 0, 1, 1, 2, 3, 5, 8, 13, and then we continue. Now, just to write this out here, this would be the 0th number, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, and then so on and so forth. So if I were to ask you to find the nth Fibonacci number, so we have some function here, say like fib, and we take in n, and we want to know what the nth number is in this sequence. Well, the way that we actually determine what each number in this sequence is we simply add the two previous values in the sequence to generate the next one. So if I'm looking for the 7th Fibonacci number, I add the 5th and the 6th together, and that gives me, well, 13. Now, same for any of the other numbers, right? So for, say, this one right here, I just add 1 and 2, and then it's an exception when you come to these first three values here because we have to have some starting values in the sequence, but for anything beyond the second number, you simply take the last number and the second last number, add them together, and that gives you the nth Fibonacci number. So the reason I'm showing this to you is because this is a great example of something that we can use dynamic programming to solve, and the reason we can do that is because we can write the Fibonacci of n as simply the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. So this is our entire problem. These are now two subproblems, and if we solve both of these subproblems, that will give us the solution to the main problem. So as easy as that, this is kind of a dynamic programming problem because we can write it in this way. So whenever you're trying to determine if you can use dynamic programming, you usually need to come up with some type of equation. It might be more complicated than this, but something along these lines where you're saying, okay, the answer to the main problem is equal to the answer of a subproblem and maybe multiple subproblems. Okay, so in this case, we're adding two subproblems together, but we could be dividing them. We could be taking the minimum or the maximum value, but we're just utilizing the subproblem's solution to actually find the solution to the main problem. So I won't drag on that explanation anymore. Now that we've looked at this, I want to show you the kind of naive approach to solving this actual question right here, so for generating the nth Fibonacci sequence, and then I'll talk about how we use dynamic programming to better optimize this solution. So I've just put on the screen here a solution to that Fibonacci problem I was just discussing, and I want to explain to you why the time complexity of the solution is very poor, and then how we can optimize it using a dynamic programming technique. Now, theoretically, you could say that this is using dynamic programming, and the reason you may say that is because we're utilizing the solution of subproblems to get the solution to the main problem. However, the issue with the solution that I have right here is that's a very horrible time complexity. The time complexity is actually big O of 2 to the exponent n. Now, I'm going to draw a diagram to explain why that is, but to quickly run through the code in case you haven't seen this before, we take in some integer n. If n is less than 2, we return n, so just for the cases of 0 and 1, so we can return 0 and 1 respectively. And then otherwise, we're returning the Fibonacci of n minus 1 plus n minus 2, and this is a recursive call, right? So I'm recursively calling the function with, in this case, let's say I had n5, this would be 4, and this would be 3. I would then have to repeat the code for those recursively, and I would get my solution. So the issue with this is that if I do decide to, say, generate the Fibonacci number of 5, or the 5th Fibonacci number, the recursive calls that I end up making is to 4 and is to 3, right? As I said, I need to call 4 and I need to call 3. Now from 4, I need to make a call to 3, and I need to make a call to 2, because if I pass n equals 4 here, well, to generate the 4th Fibonacci number, because this is not a base case, I must generate the 3rd as well as the 2nd, right? So you get the idea here. I'm just drawing out kind of the tree of all the recursive calls that we're going to have. From the 3rd number, however, I need to generate the 2nd Fibonacci number as well as the 1st Fibonacci number. From the 2nd Fibonacci number, this is not a base case. I need to generate the 1st and the 0th and add those together. From 1, this is a base case, so I simply return what the answer is. Now from 2, same thing. I need to generate 1 and 0. From 3, I need to generate 2 and 1. And then from 2, let's draw these a little bit weird here. It's going to be 1 and 0. So sorry about the messed up tree on the right-hand side, but you get the point. This tree is growing exponentially, and if I actually go in here, you can see that there's a ton of repeated values that I'm calculating. I'm calculating 1 a ton of different times, right? 0 a bunch of different times. 2 I'm calculating multiple times as well. 3 I'm calculating multiple times, and well, this is leading to a very poor time complexity of big O of 2 to the exponent n, because I'm doing a bunch of repeated calculations that I've already done. As soon as I calculate, say, the 2nd number, I really should just store that value, so I'm able to quickly access what the answer is. Same thing with 3, I should store that. Same thing with 4, I should store that. I should never have to do any of the right-hand side of this tree here, because I should have already had the solutions. I shouldn't have to actually make these recursive calls. So I understand it's a little bit confusing for now, but let me show you a new solution here that uses dynamic programming, and then you'll understand kind of the basics of this approach. All right, so I've just placed a new solution onto the screen here, which has a much better time complexity. This actually has a time complexity of big O of n, and the reason for that is we're using a technique here called memoization, which is something you do typically in dynamic programming problems. So as I said before, there was really no point in us continually making the same function calls, the same recursive calls, to calculate a value that we already calculated previously. So here, we're optimizing our solution by implementing a cache. Now, what is a cache? Well, a cache is just a way to store values that we've already calculated before. So in this solution, we're never going to do any repetitive calculations, and that means if I want to generate, say, the 6th Fibonacci number, it only takes me 6 total computations to generate that, or approximately 6, a linear number of computations. So let's just run through this solution and see how it works, because this is the most basic example I can give you of implementing a dynamic programming solution. So we have our base case again inside of this function. So if you have n less than 2, okay, we're going to return n. Otherwise, though, I'm going to check if n is in my cache. Now, the cache is simply a dictionary where we're going to have different keys mapped with different values, and every key is going to be one of the nth Fibonacci numbers, and then the value with that key is going to be the actual number associated with that. So maybe we have 0, 1, 1, 1, 2, 1, 3, and then this would be 2, right? So on and so forth. That's what will actually be in our cache, and I will generate this cache or kind of write it out as we go through this solution. So we have if n is in cache, then return the cache at n. So this avoids us having to do any repetitive recursive calls, because if we've already generated a value, it will be stored in the cache. And then what I'm doing here is exactly what I had in my previous solution, except this time I'm storing the solution to whatever the call was to n here inside of my cache so that I never have to generate it again, and then I'm simply returning whatever the value it is that I just stored in the cache. So for example purposes here, let's say n is equal to 5 again, and now let's draw out the tree and see how large the tree gets in this solution, as opposed to the previous one. So if we're solving the fib of 5, well, the first thing that we're going to see here is that it's not less than 2, and it is not in the cache, and so we are going to have to generate the solution to this sub-problem. So we're going to have to call 4, and we're going to have to call 3. So let's draw that out, 4 and 3. Okay, so now we're going to go to 4, and we need to solve the problem for 4. So if we say n is equal to 4, it's not less than 2, and it's not in the cache. So again, we're going to have to solve these sub-problems. We're going to have to call 3, and we're going to have to call 2. Okay, so now I call 3, and I call 2. Now let's do the call to 3. So we come to 3, it's not less than 2, not in the cache. We've got to solve these problems, 2 and 1. So we have 2, and we have 1. And then what happens is we have 2 here. Okay, we need to solve 2 because 2 is not a base case, and it's not in the cache. So we're going to call 2 with 1 and 0, running out of room, but you get the point, that's what we're calling it with. Okay, so when we get to 1 and 0, we're going to return our values. So we're going to get 1, and we're going to get 0. So now what's going to happen is we've returned these values, and we're going to say the cache at 2 is equal to, and then this is going to be 1 plus 0, which is simply equal to 1. So now I have my cache, and inside of my cache, I'm going to have 2, which is my nth Fibonacci number, and the value of this is going to be 1. So now, whenever I try to solve the sub-problem of 2 again, I'm not going to have to actually call these. I'm not going to have to solve 1 and 0. I'm just going to simply take the value from the cache because now it's stored inside of there. Okay, so now we've completed this recursive call at 2. 1 is simply a base case, so we return the value here. That's going to be 1. This value is going to be returned as 1 as well. Apologize, this is a bit messy, but hopefully you get the point. And now we're going to say the cache at 3 is equal to, and this is going to be 1 plus 1, which is 2. So now I'm going to change the cache. So now in the cache, we're going to add key 3, and it is going to have value 2. So now whenever we try to find what the nth Fibonacci number of 3 is, we'll be able to do that very fast. We just take it from the cache. Okay, then we need to solve 2. So now when we go to try to solve 2, I don't actually need to call 1 and 0. And the reason I don't need to do that is because 2 is inside of the cache. So since 2 is inside of the cache, I've now just avoided doing 2 recursive calls. And what I do is simply grab the value from the cache, which is 1, and I can return that up to 4, which is what needed that value. So we're going to return 1 there. And then from over on this side, we were returning a value of 2. So now when we get the 4th Fibonacci number, we're going to say the cache at 4 is equal to, and then this is going to be 2 plus 1, and that's going to give us 3. So we're going to insert this into the cache. So we're going to say, okay, 4, this has value 3. And now same thing, whenever we try to solve the subproblem 4 again, we can just grab the value from the cache as opposed to actually doing those recursive calls. Now finally, we go to this recursive call over here, which is for value 3. And for 3, it's inside of the cache. So I can simply return the value. So I return the value of 2. From 4, we know that this number was 3. And so we know now that the 5th Fibonacci number is value 5. We add those together, we would actually add it to the cache, and then we just return the value from the cache. Hopefully that explained how this worked, but what we were doing was storing the solution to each sub-problem as we went, and that avoided us having to do a bunch of recursive calls that we had to do in the previous solution. And if we wanted to reduce these even more, we could start the cache and say, okay, cache is equal to, then we could have something like 0, 1, and 1, 1, but that would effectively give us the exact same solution as just having if n is less than 2. But we could remove this if statement and simply add these values into the cache as well. Just noting there's kind of multiple ways to go about solving this. All right, hopefully that makes sense, but you've just seen an example of dynamic programming. We've used a technique here called memoization. Now this is a technique that's used for dynamic programming problems or within a dynamic programming solution, and all it involves is storing results that we've calculated in the past so we don't have to calculate them again. All right, so that is the first thing that I wanted to show you, the first example I wanted to go through. Hopefully that is all clear. Now we're going to get into a more difficult problem, and I'll give you a chance to solve it on your own, and then I will walk you through the multiple solutions and different ways to go about solving it, one of which, of course, is going to use dynamic programming. All right, so I've just written an array on the screen here, or a list, whatever you want to refer to it as, and I'm going to ask you the following question. I'm just going to verbalize it, so just listen, think about it, and then I will talk about how we solve it. So the question is determine the minimum possible sum of any continuous subarray in this array. So what that means is that I could have a subarray, say like this. This is a continuous subarray because all of the elements are adjacent to each other. I could have a subarray that's these elements. I could have a subarray that's just one single element, but they have to be touching. I can't have a subarray that has, say, this, this, and this. That would not be a continuous subarray, so they just have to be touching. Hopefully that's clear, but any continuous subarray, what is the minimum possible sum of any one that we have? And for this example right here, the minimum sum that we would have of any continuous subarray is -7. Now there's two possible answers here. The first answer is to take this as the subarray. The second answer would be to take this as the subarray. If you take the sum of all of the elements within these, you'll see that they both add up to -7. So that's really the question I'm asking you. Determine what the minimum possible sum is of any continuous subarray in an array. So take a second if you want. Think about how you would solve it, and then I'm going to show you the naive approach that does not use dynamic programming. Then we will talk about the dynamic programming approach. So hopefully you've taken a second to think about how you would solve this problem, because I'm going to go through a solution now. This solution that I have is the non-optimal solution. It runs in a time complexity of big O of n squared, and this does not use dynamic programming. Now this solution simply says, what I'm going to do is find every single subarray in this array, and then calculate the sum of all of those subarrays and determine what the minimum sum is. That's it. So we start by calculating all of the subarrays that start at -7, calculating the sum for all of them, and then updating this min sum variable. Then all of the subarrays starting at 3, then all of the subarrays starting at 4, all of them starting at -2, so on and so forth, and we get every single subarray that we have, calculate the sum, update this variable, and that will give us the correct answer. Now this solution is fine, it does solve the problem, there's nothing wrong with this. The issue is that it runs in n squared, and there is a faster and better way to solve this problem that involves using dynamic programming. So what I want to ask you now is, if you came up with this solution, can you think of any way to solve this problem in linear time? And at this point, I will mention, if you're unfamiliar with time complexities, I do have an entire video on them, so I'll leave it on the screen here and in the description. Anyways, think of a way that you can solve this in linear time, or big O of n time, utilizing dynamic programming. Now, you may not be able to come up with it. That's totally fine. Of course, that's why I'm here. I'm going to explain it to you. But just take a second and think, okay, can I solve this in a more efficient way? So the answer, of course, is yes. That's why I'm using this problem. But let's get rid of this, and let's talk about how we would actually frame this problem as a dynamic programming problem, and how we would write a solution that utilizes the solution to sub-problems. So when you want to solve a problem using dynamic programming, again, what you really need to think about is, what sub-problems am I going to have, and how are the solutions of those sub-problems going to help me come up with the solution of the entire problem? So I've just written a new example here, and I'm going to start walking you through how we solve this using dynamic programming. Now, in this example, we want to try to solve this using one single pass of the array. So rather than writing an algorithm right now, let's kind of try to do this as a human and figure out what values we're going to want to store and how we're going to optimize the previous solution. So again, we only do a single pass of the array, and there's no need to have a nested for loop and an n squared time complexity solution. So what I'm going to do is start here at this element, and I'm going to have some variable here. I'm going to say min sum, and this will be equal to 0, and this will just store what the minimum sum is that I've found so far. And what I'm trying to do here again is create this minimum sum subarray, or actually determine what the minimum sum is of any subarray. So I need to kind of build different subarrays as I go through here and determine what their sums are, update this value, and then figure out essentially what elements I want to be in this subarray. Okay, so I start at 20. We can kind of imagine that we can't see any of this right now because we're just looking at element 20. And I'm going to ask at element 20, what is the minimum possible sum that I can create using this element? So at every single element, the question I want to ask is, if I were to use this element, what is the minimum sum that I can create in a subarray? So if this element was in any subarray, I don't know how big or small the subarray would be, but if it was included 100%, what's the minimum sum I could generate? That's what we're asking. So in this case, at 20, we know that the minimum sum that we can make is 20. So let's just write this here, and we'll update this minimum sum variable. Really, this should have been float infinity, or just infinity before. And so this will now go to 20, because if we have a subarray that just includes this element right here, well, the sum of that is 20, okay? Now we move on to the next element, -7. Now, same question here. I want to ask, if I were to include this element, -7. What is the minimum possible sum that I could have? Now, the way that I determine that is I need to look at the minimum sum of the previous element, and I need to add that to the current element, and then compare that to what the value of the current element is. So we'd have 20 minus 7. That's going to give us a sum of 13. Or if we did not include this previous element, so if we were to start the subarray, say, right here, then we would have a sum of -7. Okay, so obviously -7 is going to be a smaller sum, so I'm going to put -7 there. And I would imagine that, okay, if I had the subarray, I would not expand my subarray to be like this. I would just start my subarray here on -7. No need for 20. That does not help me, right? It doesn't make it any more negative. -7, however, it does. Okay, so we have -7. Now the minimum sum that we found is -7, and that's if we're just using a subarray like this. Again, from here, we wanted to see, okay, should we include any of the elements prior? And we said no, because if we did, then it was going to make this a larger sum than just having the element itself. Okay, so now we have -7, and I'm going to move on to -3. So now if I'm on this element, I ask the same question. If I have a subarray that includes this element 100%, so we're going to end right here, would I want to include the minimum sum of the previous element or just this element? Well, if I were to take whatever the minimum sum is that I could have using this previous element, so including the previous element right here, then that sum would be -7. And that obviously would make this lower than -3, so I would just write -10 here. We're comparing -7 minus 3 and just the element itself, -3. Well, what's lower? Of course, -10. Okay, so let's erase this bar here. So now we move on to 9. And don't worry, I will explain this again, so it makes perfect sense. Let's just walk through the entire example. Okay, so now we're on 9. Same question from 9. If I were to have a subarray that included the element 9, would I want the previous elements in the array to be a part of it, or would I want just element 9? Well, in this case, I have 9, and I'm going to compare that now to whatever the minimum sum is that I could create by using the previous element. So again, really what I'm doing here from 9 is I'm looking at this value right here, and I'm saying, okay, if I were to include the last element, what is the minimum sum that I can create that uses the last element in a subarray? It's not just the value of the last element. It is, again, the minimum sum that I can create by using the last element in a subarray. And we know that the subarray with the last element is -7 and -3. So now when we come to 9, we say, okay, well, if we're going to use this element in a subarray, do we want it to just start here? Or do we want to include potentially some other elements? Well, I look at this -10, I say, well, that's less than 9. It's going to make this smaller. So of course we're going to include that. And now the sum that I can create at 9 is going to be -1. Now I'm not going to update my minimum sum. And in fact, the minimum sum should be -10. Sorry, I should have updated that before because, well, -1 is not less than -10. Okay, now I move over to -4. So from -4, again, we have the same question. Should we include previous elements in the array? Well, if I include this previous element right here, I know that the minimum sum I can generate that uses this previous element currently is -1. So that means I can say the -5 is going to be the sum right here. And that's, of course, going to be lower than me starting the subarray right here of just -4. Okay, hopefully this is all making a bit of sense. Continuing, we'll move over to 6. Now from 6, I ask the same question. Okay, should I include the previous element if I'm going to have this element in a subarray, or should I just start the subarray right here? Well, I want to include the previous element because -5 is less than 6, so that's going to give me a sum of 1 right here for this element. No need to update max sum. Continuing here, we're now at -9. Now at -9, I ask the question, is it helpful to me to include the previous element, which is going to be 6, or do I start my subarray right here? Well, the answer, of course, is no, I'm not going to include it. I'm going to get a sum of -9, and I'm going to start right here with this element because the minimum possible sum that I can create using this element with all of the previous elements that I have in this array is 1. And 1 plus -9 gives me a larger value than the -9 itself. So I just start at -9. Okay, lastly, I come over to 10. Now the answer here is just going to be 1. Of course, we're going to include -9 because that's going to make this lower. So now I actually know that the minimum possible sum that I can create is going to be -10. And there you go, I return that answer. Now I know this is not crystal clear, but really all we did at every single position here in this array is we asked ourselves the question, what is the minimum possible sum that I can get when I include this element in the subarray? Now the answer to that is it's either the element itself or it's the element itself plus the minimum sum that we can get when we include the previous element, because we need to have a continuous subarray. So if we're including the previous element, well, whatever the minimum sum is that it can have plus our current element, that's the minimum we could get if we included this element. And that allows us to actually not need to keep track of the different indices of the subarrays, but to determine the minimum sum by constantly updating this min sum variable as we run through the problem. Now, the dynamic programming aspect of this solution is that I am storing the solution to every sub-problem that I solved, and I'm simply taking the minimum of all of the solutions that I had, right? So all of these sub-problems I need to solve, I solve them one by one, and they actually utilize the solution to the previous sub-problems. I then take the minimum of all of those sub-problems, and well, that gives me the solution to the problem. So let's clear the screen here. And let's have a look at what the solution actually looks like in code. All right, so I've got the solution in front of me. Define my function. I have my if statement, so just handling an empty array here. And then I'm saying the min sum using element is equal to array at 0. So this is what we're going to use to actually store all of these sub-problem solutions. And then the minimum sum, well, this is going to give us the complete answer because we're taking the minimum sum of any of the sub-problem solutions, okay? We then continue here. And we say for I in range, and then we're looping through all of the elements except index 1, or except index 0, sorry, because we already handled that up here. And then we're going to say the number is equal to array at I, and we're going to generate what the current minimum is that we can create using this element. So the minimum possible subarray sum we can get that uses the current element that we're on. As I said, that's going to be the number. Let me draw this in a different color here. Or the number plus the minimum sum using element at the previous index. So if we were to include the previous element, whatever the minimum sum is that we could create using that element, we add that to the current element and we take the minimum of those two values. Okay, we then say the min sum using element dot append current minimum. And then we say the minimum sum is min of min sum and current min. And then we continue this, and well, that solves the problem for us. So this solution does run in big O of n time. However, it takes big O of n space because of the fact that we're using this array. Now, some of you may have noticed that since we're only ever looking at the last element in the array, we actually don't need to utilize an array and store every single sub-problem solution. What we can do instead is simply store the previous sub-problem solution. So let me put on the code for that and show you what that looks like. All right, so now this is the updated solution, which is going to run in big O of n time, and is going to take big O of 1, or constant space, because we've now removed the array, and instead we're just saying the min sum using the last element, and this is not an array, it's just whatever the last value was, because we only need to access the last value again, so we can just use a variable as opposed to using an entire array. Now, I'll let you read through this code, but at this point, I am finished with this video. Now, dynamic programming on its own is not extremely complicated. What's actually most difficult about it is determining how you write a problem in a dynamic programming way. So how you frame the problem in a way such that you're solving sub-problems. So that's what I was trying to illustrate to you before when I was walking through the array step by step, is that we can look at this problem and say, okay, the sub-problem that we're solving is what's the minimum sum that we can generate when we include this element. And once we start framing the problem in that way, it now becomes very easy to figure out how those sub-problems actually lead us to the optimal solution. So that's what you need to think about when you're saying, okay, can I use this problem for dynamic programming? Or sorry, can I solve this problem using dynamic programming? You need to think, what way can I look at this problem and kind of read it out such that I have sub-problems that I'm solving? And that's not always possible. And sometimes you can solve sub-problems, but those don't actually lead you to the optimal solution. So you have to rethink your approach. Anyways, with that said, I will wrap it up here. Hope you found this helpful. If you did, make sure to leave a like, subscribe to the channel, and I will see you in another one.